Welcome to this session. So, in this class what we are going to do is that we will be taking cue of wherever we have left in the last class. That in the last class we have solved a parabolic partial differential equation, which is a well posed problem in three dimension, one dimension in time and two dimension in space. Now, in this class we will be looking into the problem which is basically a 4-dimensional parabolic partial differential equation, which is 3-dimensional in space and 1-dimensional in time. It is a transient 3-dimensional problem, and please remember that whenever you will be working with a parabolic operator, then you are basically looking into a transient problem. Whenever you will be operating with an elliptical operator, then you are looking into a steady state problem. So, that has to be kept into mind. So, we are still solving a transient problem, 4-dimensional, 3-dimensional in space and 1-dimensional in time. First, let us formulate the problem. So, we formulate the 3-dimensional parabolic well posed partial differential equation. So, it will be del u del t is equal to del square u del x square plus del square u del y square plus del square u del z square. So, we have 1-dimensional in space, 1-dimensional in time and 3-dimensional in space. So, basically it is a 4-dimensional problem. So, this is a 4-dimensional problem. Transient. So, x, y, z and t, these are the 4 independent variables. Now, let us formulate the boundary conditions. At t is equal to 0, we have, it is a well posed problem. So, the boundary initial condition at t equal to 0 must be having a non-zero condition, the non-homogeneous condition. So, therefore, we assume that at t is equal to 0, u is equal to u naught, and we assume all the 6. So, there will be 2 boundaries existing on x, 2 boundaries existing on y and 2 boundaries existing on z, and all the 6 boundaries are having the Dirichlet boundary condition. That means, their values are specified at those boundaries which are basically homogeneous in order to have a well posed problem. So, at x is equal to 0 and 1, we have u is equal to 0. At y is equal to 0 and 1, we have u is equal to 0. At z is equal to 0 and 1, we have u is equal to 0. So, all the 6 boundaries, they are having the homogeneous conditions, that is basically a Dirichlet boundary condition prevailing on the 6 boundaries. So, what we will be expecting? We will be expecting an independent eigenvalue problem in x direction, y direction and z direction as well. So, if you really do that and go ahead with a separation of variable type of solution, that means that then you will be considered to be a product of 4 independent variable, will be a function of time alone, it will be a function of x alone, function of y alone, function of z alone. Now, if you substitute this equation into the governing equation, let us say what we get. So, if you really do that, you will be getting x, y, z dt dt is equal to t y z d square x dx square plus t x z d square y dy square plus t x y d square z dz square. Now, if we divide both sides by x, y, z, t, then let us see what we get. 1 over t dt dt plus is equal to 1 over x d square x dx square plus 1 over y d square y dy square plus 1 over z d square z dz square. So, the left hand side is entirely a function of time, the right hand side is totally a function of space. They will be equal and they will be equal to some constant, and this constant has to be a negative constant. If we have a positive constant or 0, then we will be landing up with a trivial solution. So, this has to be equal to minus lambda square, where lambda lambda square is a positive constant. Now, let us look into the spatial varying part. So, if we look into the spatial varying part, so we will be getting 1 over x d square x dx square plus 1 over y d square y dy square plus 1 over z d square z dz square is equal to minus lambda square. Now, as we have seen earlier that as far as the boundary conditions are concerned, we are having homogeneous boundary conditions, both homogeneous boundary condition in the x direction as well as the y direction and z direction. So, therefore, we will be formulating a standard eigenvalue problem in these 3 directions independently. So, let us look into the formulating the standard eigenvalue problem in the x varying part. So, 1 over x d square x dx square is equal to minus lambda square minus 1 over y d square y dy square minus 1 over z d square z dz square, and the left hand side is a function of x alone, the right hand side is a function of y and z alone. So, therefore, they will be equal, and this equal, they will be equal to some constant, and this constant has to be a negative constant in order to have a standard eigenvalue problem in the x direction. So, let us formulate that d square x dx square plus alpha square x will be equal to 0. This will be the first eigenvalue problem in the x direction, and the boundary conditions of the original problem would have been satisfied by the boundary condition of the x varying part. So, at x is equal to 0 and 1, we have capital X is equal to 0. So, this has been done, and we have already seen the solution of this. The solutions are alpha n is equal to n pi at the eigenvalues, where n runs from 1 to infinity. So, these are the eigenvalues, and eigenfunctions are sine functions. X n is equal to constant, let us say C 1 sin n pi x. Okay. So, let us formulate the y varying part. So, if we look into the governing equation, minus lambda square minus 1 over y d square y dy square minus 1 over z d square z dz square is equal to minus alpha square. So, I take y varying part on the other side and bring minus alpha square there. So, 1 over y d square y dy square should be is equal to minus lambda square plus alpha square minus 1 upon z d square z dz square. So, the left hand side is function of y alone, the right hand side is a function of z alone, and they are equal, and they will be equal to some constant, and again this constant has to be a negative constant, otherwise we will be landing up into a trivial solution. So, therefore, this will be is equal to minus beta square. So, we will be having the standard eigenvalue problem in the y direction, d square y dy square 1 over y plus beta square is equal to 0, and the standard eigenvalue problem in the y direction becomes plus beta square y is equal to 0 at y is equal to 0 and 1, capital Y is equal to 0, because the boundary conditions of the y varying part should be satisfying the boundary condition of the original problem in the y direction. So, in the original problem, the boundary condition in the y direction were Dirichlet, and they were equal to 0 at y is equal to 0 and 1. Similarly, therefore, the y varying part must also satisfy that. So, we know the solution of this, since it is an independent eigenvalue problem, the index will be m. So, beta m is equal to m pi, where m is equal to 1 to up to infinity, and these are the eigenvalues and eigenfunctions are y m is equal to C 2 sin m pi y. Now, let us look into the z varying part. So, if you look into the governing equation, minus lambda square plus alpha square minus 1 over z d square z dz square is equal to minus beta square. So, I take z varying part to the other side and bring beta to the left hand side. So, if you do that, you will be getting 1 by z d square z d z square is equal to minus lambda square plus alpha square plus beta square. So, they will be a combination of constant, and again this constant must be a negative constant, otherwise you will be landing up with a trivial solution. So, this constant must be equal to minus gamma square. So, we will be having d square z by dz square plus gamma square z will be equal to 0, subject to the boundary condition at z equal to 0 and 1. We have capital Z equal to 0, and we know the solution of this. Solutions will be the will be a p pi, where index p runs from 1 to infinity, and the eigenfunctions of the sine functions. So, gamma p will be is equal to p pi at the eigenvalues, where p runs from 1 to 3 up to infinity, and z p will be nothing but C 3 sin p pi z. Okay. Now, let us look into what is the value of lambda. So, this is the governing equation of lambda. So, if you take on to the lambda to the other side and gamma to this side, what we will be getting is that lambda square is equal to alpha square plus beta square plus gamma square. So, we have seen alpha is equal to n pi, beta is equal to m pi, and gamma is equal to p pi. So, therefore, lambda square will be nothing but m square plus n square plus p square pi square, and lambda should be with a subscript written as a subscript m, n and p. So, now we look into the time varying part. So, if you look into the time varying part, we write is as 1 by t dt dt is equal to minus lambda m n p square, and since we are using the subscript m and p, the corresponding solution is also t m n p. So, therefore, we have the solution t m n p as equal to C 4 exponential minus lambda m n p square of that time t, where lambda m n p is given by this expression. Now, we are in a position to construct the complete solution of u as a function of x, y, z and t. Now, if you really do that, so there will be appearing 3 summations, because we are having 3 independent eigenvalue problem. So, u x, y, z and t will be nothing but summation, triple summation 1 over m 1 to infinity, another over n 1 to infinity, another over p 1 to infinity. There will be 4 constants to be multiplied. they will be giving rise to a new constant. So, we write down the constant as CMNP exponential minus lambda MNP square of that times t sin n pi x sin m pi y sin p pi z. Now, the problem is almost over. Only one constant C m n p has to be evaluated. This constant has to be evaluated from the unused initial condition of the original problem, that at t is equal to 0, u is equal to u naught. So, utilizing that initial conditions, the non-homogeneous initial condition at t equal to 0, u is equal to u naught, we will be able to evaluate the constant C m n p. So, if we do that, let us see how we will be obtaining the constant C m n p as u naught is equal to summation triple summation 1 over m another over n another over p C m n p exponential minus lambda m n p square of that t sin n pi x sin m pi y sin p pi z. Now, since we will be having the three standard eigenvalue problem in this particular partial differential equation, we will be utilizing the orthogonal property of the eigenfunctions. That means, we will be multiplying both sides by the sin m pi x sin n pi y sin q pi z, and integrate over the domain of x y z. And after doing that, if you open up this summation series, only one term will survive on the right hand side when m is equal to n and n is equal to m and p is equal to q. So, therefore, what we will be getting is u naught triple integral 1 over x from 0 to 1 y 0 to 1 z 0 to 1. So, sin n pi x sin m pi y sin p pi z dx dy dz, and on the right hand side only one term will survive, that will be C m n. So, this will be equal to 1 at t is equal to 0. So, at t equal to 0, this will be equal to 1. So, we will be on the right hand side, you will be getting C m n p integral sin square n pi x dx 0 to 1 sin square. So, this is at t equal to 0 sin square m pi y dy multiplied 0 to 1 sin square p pi z dz. So, u naught, the first one integral sin n pi x dx, it will be nothing but 1 minus cosine n pi over n pi. The second one integral sin m pi y dy will be nothing but cosine m pi over m pi. The third one integral sin p pi z dz will be nothing but 1 minus cosine p pi divided by p pi is equal to C m n p, and sin square n pi x dx we have already seen it is half, this will be half, this will be half. So, we will be getting 1 by 2 into 1 by 2 into 1 by 2. So, C m n p will be nothing but 8 u naught pi cube 1 minus cosine n pi 1 minus cosine m pi 1 minus cosine p pi divided by m n p. So, that will be the expression of C m n p, and we are coming closer to our complete solution, and the complete solution is that u x y z and t will be nothing but triple integral 1 over m n p exponential minus lambda m n p square t sin n pi x sin m pi y sin p pi z. There is a constant C m n p, where lambda m n p square is nothing but m square plus n square plus p square times pi square, and the constant constant C m n p is equal to 8 u 0 over pi cube 1 minus cosine n pi 1 minus cosine m pi 1 minus cosine p pi divided by m n p. So, that gives the complete solution of a well posed parabolic 4-dimensional partial differential equation. And if we and this can be, if we look into the, if some of the boundary conditions are altered. Now, in this particular problem, all the boundary conditions are Dirichlet boundary condition. Now, if we have a Neumann boundary condition in one of these directions, that means let us say at x equal to 0 and y equal to 0, and let us say Dirichlet boundary conditions are prevailing in the z direction. Now, the cosine functions will be eigen functions in some of the cases, corresponding cases, and the eigenvalues will be different. For example, if we take up another example of this sort, that del u del t is equal to del square u del x square plus del square u del y square plus del square u del z square, and at t is equal to 0, u is equal to u naught, at x is equal to 0, we have let us say del u del x is equal to 0, let us say the boundary is insulated there, and x is equal to 1, u is equal to 0. This is the boundary at x is equal to 0 on the x direction. At y direction, at y is equal to 0, u is equal to let us say 0, and y is equal to 1, u is equal to 0, and at z equal to 0, we have let us say del u del z equal to 0, and at z equal to 1, we have u is equal to 0. So, this will be the small z. Okay. So, let us look into the solution of this problem. In this problem, instead of Dirichlet boundary condition in all the boundaries, we have a Neumann boundary condition prevailing at x is equal to 0 and z equal to 0. Now, let us see how this problem can be solved. Now, we will be again looking for a separation of variable type of solution, and we consider that u is a function of product of 4 variables, which will be a sole function of time, which will be a sole multiplied by sole function of x, multiplied by sole function of y, and multiplied by sole function of z. If we do that and put this equation in the governing equation, and then separating the variables, the final expression we will be getting is 1 over t dt dt is equal to 1 over x d square x d x square plus 1 over y d square y d y square plus 1 over z d square z dz square. And again, as you have seen earlier, the left hand side is entirely a function of time and right hand side is entirely function of space, and they will be equal to negative constant minus lambda square. Now, let us look into the spatial varying part. The spatial varying part will be 1 over x d square x dx square will be nothing but minus lambda square minus 1 over y d square y dy square minus 1 over z d square z dz square, and left hand side is entirely function of x, right hand side is a function of y and z. They will be equal to some constant. This constant will be minus alpha square. So, we will be having a standard eigenvalue problem in the x direction as d square x dx square plus alpha square x is equal to 0, subject to the boundary condition of the original problem in the x direction at x is equal to 0, dx is equal to 0, because the gradient del u del x was 0 in the original problem at x equal to 0, and at x equal to 1 we had x is equal to 0. So, you know the solution of this problem. The eigenvalues are 2n minus 1 pi by 2, alpha n is equal to 2n minus 1 pi by 2, where n runs from 1 to infinity, and eigenfunctions are x n c 1 sine, there will be cosine functions. So, cosine alpha n x. Now, that completes the x varying part. Now, let us look into the y varying part. Minus lambda square minus 1 over y d square y dy square minus 1 over z d square z dz square is equal to minus alpha square. So, therefore, minus 1 over, so we take this one to the other side. So, 1 over y d square y dy square is equal to minus lambda square plus alpha square minus 1 over z d square z dz square. So, again the left hand side is a function of y, the right hand side is a function of z only, that will be equal to some negative constant in order to get a non trivial solution. So, the governing equation of y will be simply d square y dy square plus beta square y will be equal to 0. And in the original problem, we have seen that the Dirichlet boundary conditions are prevailing in the y direction. So, therefore, at y is equal to 0 and 1, we have capital Y is equal to 0. So, I will stop in this class. In the next class, I will be completing this problem and then we will be moving ahead with the solution of elliptical partial differential equations, which are quite common in all engineering applications which are occurring under steady state. Thank you very much.